Thank the group for this opportunity to share our results. So in this presentation, I'll talk about coverability of subshifts. So this is joint work with Manuel Loquias and Eden Miro. So let's begin with the definition of coverable words. So a finite word over an alphabet. So all throughout this presentation, our alphabet will be a finite alphabet. So a finite word W over a finite alphabet is coverable if for some proper subword U of W is formed by overlapping or adjacent occurrences of our U. So this property of words can be viewed as a generalization of periodicity since it allows not only concatenations of U, but also overlaps between consecutive occurrences of U. Equivalently, a finite word U is coverable if U here covers every position in our word W. So here in our example, if we look at this position of our word, it is covered by some occurrence of the word AABA. And so we say that our word is AABA coverable. So W will be referred to as the cover of. So U here is referred to as the cover of W. So this definition is extended naturally to define coverable right infinite and by infinite words. So in some literature, this property of the words is termed quasi-periodicity, as first used by Apostolico and Ehrenfeucht in 1993 when they studied quasi-periodic finite words in the context of text algorithms. In our study, we used the terminology used by Gamard and Richomme in 2015. So let's look at an example of a by infinite coverable word. So here we have the Fibonacci substitution defined on the alphabet of two letters consisting of letters A and B, where A is sent to AB and B is sent to A. So the by infinite word W, that is the fixed point of the square of the Fibonacci substitution, it's ABA coverable. In fact, all of the elements in this set are also ABA coverable. So we know that all elements of the Fibonacci substitution, so all elements of this set are Sturmian. And so what we have here are examples of by infinite Sturmian words that are coverable. So before we proceed, I'd like to remark some of the notations used in this slide. So first remark is on the map S. So the map S here is the shift map on the set A to the Z. So this is, so under S, W is, so under S, we shift the letters of W one position to the left. The set A to the C forms a metrizable space under the product topology when our alphabet A is equipped with the discrete topology. And so when we take the closure of the orbit under the shift map, we do so by looking at it as a subspace of A to the Z. So the set here is referred to as the subshift X associated to our substitution phi. We can also refer to it as the subshift generated by our by infinite word W. Okay, so again, what we have here are examples of by infinite Sturmian sequences that are coverable. But last year, in 2020, Barbero, Gamard, and Grandjean was able to show that each by infinite Sturmian word has in fact an infinite number of cover. So this is one of the difference between the coverability of right infinite words and coverability of bi-infinite words, because in the case of right infinite Sturmian words, not all right infinite Sturmian words are coverable. This was shown in 2004 by Levy and Richaud. Okay, so some motivations of our study are the works by Levy and Richaud that links coverability of right infinite words and the morphisms that generate them. So we wish to answer, at least partially, a problem they posed in 2013, but in the context of bi-infinite sequences. So first we look at what would happen to the subshift generated by a coverable bi-infinite word W. So it happens that when W is bi-infinite and coverable, all elements in the subshift it generates are coverable as well. So in particular, if we have a finite word U that covers W, our word U will cover all other elements of the subshift. Okay, so presented here is the outline of the proof. So first, we'd like to note that the shift map preserves coverability in RA to the Z. So this is another difference between the study of coverability of right infinite words and bi-infinite words. Because in, so if we want to look at only the, what happens to the orbit of coverable right infinite sequences, not all of the elements of that of its orbit under the shift map would be coverable. However, for bi-infinite sequences, if our W is coverable, all elements of its orbit under the shift map would be coverable as well. Okay, so next we went on showing that every limit point of the subshift is coverable. So first, we considered a set of elements in the orbit of X, so each of which would be coverable by the previous, by the first remark. And we want, so if K is the limit of this sequence, we want, for any position I of X, we want K large enough so that the position I will be contained in some interval of length 2 times the length of U minus 1. So U here is a cover of W. So for any position I, we want it to be contained in on an interval of this length. Because if we have a U coverable word, any subword of at least of this length, an occurrence of U is assured. And so with that, every limit point of the subshift is coverable. Okay, so because of the previous result, this led us to define what do we mean by a coverable by infinite subshift. So a subshift, a by infinite subshift is said to be coverable if there is a coverable by infinite word X that generates the subshift X. So the a finite word U is said to be a cover of the subshift if it covers all of the elements in the subshift. So in 2004, Montil and Marcus defined coverability, coverable right infinite subshift in a similar manner. So if we have, so instead of being a subset of it to the Z, so if we have a right infinite subshift X, it's coverable if we have a right infinite W that generates our X. Okay, so now being a property of subshift, we wanted to know if coverability of subshift is topologically invariant. or is preserved under conjugacy. So unfortunately, we were able to have an example which proved that coverability of subshift is not topologically invariant. So we have here a bi-infinite sequence W. So this is AAB coverable. And so by the previous result, the subshift it generates should contain all the elements of the subshift it generates should be ABA coverable as well. So if we are to get the image of W under the fourth block code defined here, unfortunately, its image under the fourth block code gives us this sequence that is not coverable because if this is coverable, the cover must contain all digits 1 to 5, but there is only one occurrence of 2 and 3, and so there is no proper subword that would cover the positions 2 and 3. These positions of 2 and 3. And so the image of this subshift under the fourth higher block code would not be coverable. Okay, so in anticipation for the next result, I'd like to give a remark on the covers of RW. So RW here has two types of covers. One is of the form A concatenated with n copies of ABA, and the other type is of the form we have n copies of ABA concatenated with the letter A. So our word W here has only these types of cover. So if the cover falls under this type is not left special, but is right special. So what do we mean by left special and right special factor? So so briefly, let's recall, we say that a subword is left special if it can be extended in at least two different ways on the left. It's right special if it can be extended in at least two ways on the right. Okay, so this word, so this cover is left special because it can either be preceded by a letter B or a letter A on the left. So this is left special, but it is not a right special because it is always preceded by, let me correct. So this subword here is always preceded by the letter A, and it can be followed by the letter A and by the letter B. And so this is not left special, but it is right special. Meanwhile, this subword is always followed by the letter A, so it is not right special, but it can be preceded by the letters A and B, and so it is left special. So what I'm saying here is that all covers of W is either left special in W or it's right special in W. So because of our observations, because of these observations, we want to define a special type of coverability called the non-special coverability of subshift. So if our coverable subshift has a cover that is not left special and not right special in any element in the language of our subshift, then we say that the subshift is that the subshift is non-special coverable. So in our previous example, we were able to show that the Fibonacci substitution subshift is coverable, and it is non-special coverable because we were able to so there is a cover of the Fibonacci subshift that is uniquely that can be uniquely extended to the left by A and uniquely extended to the right by the letter B. So here, the word BAA is a cover of the Fibonacci subshift. It covers all elements in the subshift, and it is uniquely extended to the right and to the left. So we have a non-special cover of the subshift. And so the Fibonacci subshift is referred to now as the Fibonacci subshift has a non-special coverability. Okay, so by looking at that special type of coverability, the non-special coverability, we were able to show that if we have two primitive substitutions, phi and gamma, such that its associated subshift are topologically conjugate to each other, then one subshift is non-special coverable if and only if the other is non-special coverable as well. So here is an outline of the proof. So I'd like to define the substitutions that we used. So so the B sub i's here are the ith higher block code. So we considered one higher block code earlier when we looked at the coverability of the Fibonacci substitution. So for the one block code here, the existence of such one block code that commutes our diagram is assured by a classic theorem by a classic theorem in shift dynamical systems. So if this is a one block code and what we have here is a shift that is coverable because of the one-to-one letter-to-letter substitution, this subshift is also coverable. In these directions, it's better to illustrate using an example. So let's consider an example, the Fibonacci substitution. So earlier, we remarked that U here is a non-special cover. It's uniquely extended to the left with a letter A and uniquely extended to the right with the letter B. So what do we mean by a one colored substitution? So when we have a one colored substitution, we want to, if we have the letter B, we want to take note one letter to its left and one letter to its right. So this will be, so A here is the left color of B, and A here is the right color of B. And so if our n is equal, so if we have n equals to 1, then we want to consider all of the three legal letters in our subshift. So in the Fibonacci subshift, all the three legal letters would be all the blocks of length 3 legal in the subshift are ABA, BAA, AAB, and BAA. So if the extreme left and extreme right letters are the colors. And so we have B as our the main letter that we will consider when we are to get the image of this new alphabet. So the one colored substitution induced by the Fibonacci substitution will be defined on this new alphabet. And we want to take the image of the middle letters under the Fibonacci subshift. So B is mapped to A is mapped to AB. And for the colors of the letters in the images, we have to take note of the left end of our right color. So the right color here is B. So for example, the right color here is B. So the left end of the image of B under phi is the letter A. And if we are to get the the left color here, which is B, the image under phi would be A. And so exactly we have A as the left color of our left color of our letter A here. Okay, so we can also denote the one colored substitution, Fibonacci substitution in this manner. So by representing this letter in our new alphabet as 0, this new letter as 1, 2, and 3. So in the proof, you want to find using the non-special cover of our Fibonacci subshift, we will construct a cover for the subshift generated with the n-colored substitution. So if our n is equal to 1, the unique letter that precedes our non-special cover would be enough to construct our cover. Also, the unique letter that succeeds our non-special cover is enough to be able to construct as a cover for this subshift. Okay, so representing this subword in the subshift. So again, we have to take note the one letter that precedes and that succeeds a particular letter in U. So B here is the first letter in U, and it is preceded by A and succeeded by B. We have the letter A here, which is preceded by the letter B, excuse me, and succeeded by the letter B. And so what we have here is actually a cover of our associated subshift, associated with the one colored substitution. So what happens if our n is greater than 1? So if our n is greater than 1, we want to construct a cover that can be extended at least n digits to the left and n digits to the right. So in order for us to construct such a cover, we simply get the image of these unique letters under some kth iteration of our substitution. Okay, so if we are to get if we have our U here, it's uniquely preceded by A, uniquely succeeded by B. We want to get the image of this cover under some kth iteration of the substitution. So how would we know the value of K? So what we want is for K large enough so that the colors of every digit in this word will be contained here. So we want K large enough so that the image of beta under the kth iteration of phi is at least of length n. So to construct a cover for the subshift associated with the n colored substitution, we want to look for a value of K such that this is true. So the value of K here always exists because if we have a primitive substitution, the length of the images of any letter as K increases also increases without bound. And for this direction, what we want is to, so once we do have a cover for the for this higher block code, we want to simply forget the covers. So here, if we are to forget the if we are to forget the colors, what we get is precisely our original word W, which is B, BAA, BA, BAA. Okay, so among the results of Levy-Indershom on coverability of subshift, right infinite words is the link between the coverability of right infinite Sturmian words and the morphisms that generate them. So in their work in 2007, they considered morphisms that are called quasi-periodic morphisms. So a morphism from an alphabet A to B, it's said to be quasi-periodic if for any coverable word W, the image of W under the morphism is also coverable. So they further classify this type of morphisms as either strongly quasi-periodic or SQP, weakly quasi-periodic or WQP, or it's a quasi-period free, or we denote it here by QP free. So a quasi-periodic morphism is said to be strongly quasi-periodic if whenever W is non-coverable, its image is still coverable. A quasi-periodic morphism is said to be weakly quasi-periodic if for some non-coverable W, its image under phi, it's coverable. Meanwhile, the morphism is said to be quasi-period free if whenever W is non-coverable, its image under var phi is non-coverable. Some examples of these types of morphism are listed here. So if we have the square of the Fibonacci substitution, it is SQP on it's SQP on the by infinite words. But the Fibonacci substitution itself, it's weakly quasi-periodic and not strongly quasi-periodic on the by infinite words consisting of A and B. And lastly, we have here a substitution phi that is QP free on right infinite sequences consisting of letters A and B.
Sorry, Jane, I'm really sorry, but you're out of time.
Oh, okay. I'm sorry.
Maybe just a couple of minutes for the summary of the rest.
Okay, so I have 2 slides left. So one of our goals is to relate SQP, the types of quasi-periodic morphisms on the right infinite sequences to the by infinite case. So in the work of Levy and Rishom in 2013, they were able to show these assertions on the SQP on finite WQP and finite, SQP on right, and WQP on right infinite sequences. So one of our goal is to relate SQP on bi-infinite sequences and WQP and bi-infinite sequences to the previously considered morphisms. So in this diagram, the dashed arrow are not true if we have an X here. While if there is no X, that assertion is true. That ends my presentation. Thank you for your attention.
Thank you. So maybe we have a time for a very brief question. Somebody has it. If no, then thank you, James, and we have to continue with the next speaker. Thank you.
Thank you.